So I want to go through another example of reduction by order. We're going to go through the entire process, and then I'm going to show you how to come up with that Y2 solution using the formula. So we're going to go through the same kind of thing we did with the last one. So we are going to let, this is Y2, be U times Y1. And our Y1 is X squared. So I'm just going to call this Y just to cut some notation here. So first derivative, product rule, first times derivative of the second plus second derivative of the first. Clean that up. And then Y double prime. I'm viewing this as first and second. So first times derivative of the second plus second times derivative of the first. Same thing here. First, second function. First derivative of the second plus second derivative of the first. So I'm going to clean that up just a little bit. Y double prime is 2u. And then notice we have 4 of those. U prime x's plus u double prime x squared. So now we're doing a substitution into the differential equation. The differential equation is x squared times y double prime minus 3x times y prime plus 4y is equal to 0. So we're going to distribute. So let's see if anything is going to reduce. So those terms are going to cancel out. So we are left with u double prime x to the 4th plus u prime x cubed is equal to 0. And if we divide everything by x to the 4th so that it's in proper form, there we are. So this is where we're going to do our substitution. We're going to let w equal u prime. So w prime equals u double prime. If we substitute in, we have that. This is another one we can probably separate the variables. Or we could approach it as first order linear. So I'm going to move the ln's to the same side and then combine them. So we have e to the c is equal to wx. E to the c is just a constant. So I'm going to call this c1 over x. There's my w. So we have w equals c1 over x. So then we're going to do another substitution. W, if you remember, was u prime. Separate, integrate. And if you remember, we need a substitution for u now. So I'm going to go all the way back up to the top. We said that y is equal to u over x squared. So that means y over x squared is equal to u. So there's our substitution for u. That's going to go in down here. So y is equal to c1 x squared ln of the absolute value of x plus c2 x squared. So we started with the x squared. This guy was y1. Our y2 is x squared ln absolute value of x. So that was reduction of order. Now, if we wanted to use that shortcut formula to get y2, let's recap that. So it's going to be y1 times the integral of e to the negative integral of p dx over y1 squared times dx. So our y1 was x squared. We've got to figure out what our p of x is. So we're going to go back up here. So our differential equation was this. And if we divide everything by x squared, we can see that p of x is negative 3 over x. Y1 was x squared. So this is going to be e to the 3 integral of 1 over x dx over x to the 4th. So we have x squared outside. This is going to be e to the 3 ln of x over x to the 4th. And that is e to the ln of x cubed in the numerator. And that's going to reduce to just x cubed. So I have x cubed over x to the 4th. I need to simplify. And that is 1 over x. And when we integrate 1 over x, we get the ln of the absolute value of x. So there's our y2. So then the general solution would be c1 y1 plus c2 y2. So you can see how we can use both ways to get that. So I want you to notice the difference between using that formula for a reduction of order and doing the process of reduction of order. So reduction of order is going to give you the final solution, right? You just may have to rewrite those constant values. That's what happened in example 2 here. We got that final solution. And then the same thing with example 1, and we ended up with that final solution. That integration formula only gives you the y2, and then you've got to use your superposition principle to find that final solution, which is the general solution. In both of these examples, example 1 and example 2, we had homogeneous differential equations. Now we're going to do a non-homogeneous differential equation. So let's look at 20. So in this one, we don't have a choice. We can find y2, but we're also going to have that particular solution for that non-homogeneous part. And the only technique we have in our toolbox right now, so to speak, is reduction of order. So we have to go through that entire process to solve this. So let's start. We're going to start by saying we're going to let y equal uy1, which in this case is going to be u times e to the x. So then y prime is the derivative of that. First derivative of the second plus second derivative of the first. Second derivative is the second derivative of that. So product rule on both of those. First derivative of the second plus second derivative of the first. First derivative of the second plus second derivative of the first. Combining like terms, we have u e to the x plus 2u prime e to the x plus u double prime e to the x. So now we're going to do our substitution. And we're substituting everything into this differential equation for those pieces. So we have y double prime minus 4 times y prime plus 3y is equal to x. I'm going to distribute and then try to simplify. So let's see what we can reduce. We have some u e to the x's. It looks like they're all going to cancel. And then we can put the u prime e to the x's together. So we are left with u double prime e to the x minus 2u prime e to the x. And that's equal to x. So proper form, we need to divide everything by e to the x. And when we do that, the e to the x divided by e to the x would cancel there. And we're going to have x over e to the x, which is x e to the negative x. Okay, notice this is not homogeneous. We will not be able to separate this. We will have to use first order linear techniques. So we're going to do our substitution now. And we are going to let u double prime equal w. So u prime is w prime. So when we substitute in here, w prime minus 2w is equal to x e to the x. We need to find our integrating factor. So there it is, e to the negative 2x. We're going to multiply through. we're going to do a rewrite. So we have d over dx. This is integrating factor times w. And that's going to be equal to x times e to the negative x. Hold on 1 minute. We have dropped a negative from here. This should be a negative here, which would make this a negative here. Be careful with your negatives. So now we have e to the negative 3x here. Make those corrections on your notes. It's easy to miss a negative. Now this is where we do our check. If we take the derivative with respect to x of e to the negative 2x times w, that's first derivative of the second plus second derivative of the first. You can see how this is equivalent to that, which means we have the correct form here. Should always double check that. So now we can multiply by dx and integrate. So we have e to the negative 2x times w equals this integral. Now that's going to require by parts. So I'm going to do by parts over here. So we're going to let u be x, so du is dx. That means dv is e to the negative 3x times dx. And if we integrate that to get v, we're going to have negative 1/3 e to the negative 3x. So applying by parts to integrate this piece, we're going to have uv minus the integral of v times du. So I'm going to simplify before I integrate this. I'm going to pull that 1/3 out. So we have this 1/3 hanging out here. So when we integrate this, remember we're missing a negative 3 here, and we would compensate with a negative 1/3 here. So when we integrate that, we're going to have times a negative 1/3 out here. Negative 3x plus c. I'm going to simplify. I'm just going to use c1 there. So now if we move this term to the other side, we can do it by multiplying by e to the 2x. So here's what I'm thinking. I'm multiplying by e to the 2x. So that's going to give me an e to the negative x here, minus 1/9 e to the negative x, plus c1 e to the 2x. So now we need to do our second substitution. We said w was u prime. So when u prime is du over u, separating the variables, And then integrating gives us u on the left. I dropped the x. There should be an x there. So we get to do by parts again on that. So I'm going to do that off to the side. So if integrating negative x over 3 e to the negative x, here's the way I'm going to view that. I'm going to view that as a negative 1/3 times x e to the negative x dx. So this is what I'm completing by parts on. So u is going to be x, dv is e to the negative x dx. So that means du is dx, and v is negative e to the negative x. So when I integrate that, I have negative 1/3 times uv minus the integral of v du. So when I integrate this is a u substitution. This is part of my du. So that's the integral for this guy. So I have 1/3 x e to the negative x plus 1/3 e to the negative x. So to integrate this one, that's another u substitution, so I'll write it out over here. I'm now integrating negative 1/9 e to the negative x. So here's the way I'm going to view that. I'm going to pull the 1/9 out, but I'm going to leave the negative in there because that's part of my du. There's my du. So I'm going to have a positive 1/9, and when I integrate e to the u, I'm going to get e to the u. And then when I integrate that last one, which is just that c1 times e to the 2x, I would need a 2 right here, and I would compensate with a 1/2. And then we would have a plus c on the end. So now I'm going to copy that to the next page so we can finish the problem. So we need a substitution for u. In the beginning, we said y was equal to u e to the x. So that means y over e to the x is equal to u. And we could put those together. I'm just going to wait till the end. Multiply everything by e to the x to get y by itself. So we're going to have 1/3 x plus 1/3 plus 1/9 plus C1 over 2e to the 3x plus C2e to the x. So final answer, we have 1/3 x plus, what was that, 4/9, plus, this is another constant, I'm just going to call it C3, e to the 3x plus C2e to the x. So there's our final answer. Now we started with e to the x is y1. So there's our y1. That means this guy has to be y2 because that's the piece that's connected to another constant of integration, which means that this is that particular solution. So there's our final answer. This is the general form of this solution for this differential equation.